All right, welcome back. This is now lesson 2.3. Why am I writing with the mouse? I should be writing with the pen. This is now lesson 2.3 notes. Um, this is all about predicting the shape of distributions. So we've got, obviously, we aren't able to produce these graphs in class, which the way that we would have produced these if I was there would be I would hand out dice to everyone, I would hand out pennies to everyone, and then I would hand out a bunch of stopwatches. All of these are things that I have, of course, but I'm not in class to even use them. So what we would do is we would have each person test and do three of these, and then we would record the data, and then everyone would kind of combine all of their data in one place. So the prediction of the histogram, this is actually like what you would be drawing. This is your prediction of what you think the data would look like. And then the actual histogram is what would actually happen based on the information, based on the collecting of all of the data together. So I'm going to go through and more or less explain why these have their particular shapes. So first off, we were starting with dice rolls. It's probably pretty simple to understand where you may think that you're rolling different amounts of each number. Um, if you roll enough times, it will actually end up being just completely flat. It takes a lot of rolls to get there, but you eventually, and you'll find the actual histogram will in fact be just flat across the top. This is what's known as the uniform distribution. The uniform distribution is like skewed left or skewed right. The uniform is just that it's flat across the top. So you have this flat um, distribution here, and the mean and the median are about the same. That's kind of an advantage to a uniform distribution. It's a lot like the a symmetrical distribution. Because technically a uniform distribution is symmetrical because you can fold it on itself and it will be just a perfect copy on each side. These are what are known as density curve. Everything that we're talking about here. These are what are known as density curves, and a density curve has a total area of 1. So in the case of the prediction, it probably adds up to 1 because that's how many rolls you did, right? So however many rolls here plus these plus these plus these plus these plus these would equal the total number of rolls, and therefore you could do relative frequencies. We talked about this a couple weeks ago. You could take the relative frequencies and add them up, and they should total like 1.0 or 0.99, depending on how you round. Um, this actual histogram, though, you'd end up with 1 over 6 is the probability for each like bar. Well, you end up with 1 over 6 for all of them. And this 1 over 6 times ends up giving you 6 out of 6, or an area of 1. All right, so for number 2, we'd be tossing pennies and trying to make them land on a target. I probably would have um, put like a poster or something on the floor and then we try that, but obviously we couldn't do that. So you'd probably predict something along the lines of this, where you think that it should be more or less symmetrical. And then on average, you'd be like between 20 and 30 centimeters away from the target. But what you would find if we actually did this in person is that most people are a little bit better than that, and you would end up flipping or tossing this penny a lot closer to the target than an average of like 25, right? So you would end up a little bit closer than that. And so what you would find was that you'd have some people that are just awful at this. You'd have some people that cannot um, cannot throw this penny to save their life. So those people would be considered outliers on the high end, but you'd find that most people would be able to be reasonably accurate in throwing this penny, which is what brings the distribution to be skewed right instead of symmetrical like this. And number three, this is trying to stop your stopwatch at exactly 5 seconds. Um, record what the stopwatch reads below. Okay, so what you would find is you would probably think um, that most people would undershoot this 5 second mark. So they would actually click the button too early. And if you're undershooting that 5 second mark, then you'd end up with a distribution that is approximately skewed left or roughly, sorry, skewed right. You'd end up with a distribution roughly skewed right. But in this case, you'll find that people are just as likely to undershoot that 5 second mark as well as overshoot that 5 second mark. So you end up with a distribution that is approximately normal. And this is a phrase we haven't heard yet, but don't worry, we'll get there. So on average, they're going to get it about 5 seconds, and then obviously there's some people that are going to way undershoot, some people that'll way overshoot. That's just how it is. So I'm going to go ahead and zoom in on this part. You can go ahead and pause now if you want to copy this down. So what we've got is density curves. The area will always total to 1. This is not some kind of special case. This always happens. The area underneath any curve, any density curve, is always equal to 1 or 100%. We have this special kind of distribution known as a uniform distribution. That's when it's just flat across the top. We have symmetric, where the mean is approximately the median, skewed right, where the mean is bigger than the median, and skewed left when the mean is smaller than the median. Everything here in LT2, we've already talked about this. If you do the chicken wing thing, where you reach out and grab with either hand, point your thumb. It is mean, median, mode in that order. So that helps you remember the relationship in between the mean and median based on which direction it is skewed. And then LT3, this is something we haven't talked about yet. So this is your first introduction officially into the normal distribution. The normal distribution is a density curve that is symmetric, single-peaked, and bell-shaped. We describe a normal distribution using the mean and the standard deviation. So the mean and the standard deviation will describe a normal distribution. Um, there is no other form of normal distribution other than the standard normal distribution, which is what you use z-scores for, which is this formula, which I believe we saw on the notes on Monday and the 2.1 notes. So I'm going to go ahead and stop here. I'm going to show you the answers to kind of the more challenging questions here. Of course, if you have questions, reach out to me on Remind, or we'll talk about them when I get back.